Let us try to understand what equilibrium is through a simple observation. Look at the closed container with a small amount of liquid bromine. What do you observe? You observe that some of the liquid bromine is evaporating to an orange vapor, and slowly the vapor becoming thicker. After some time, you can see that there is no change in the intensity of the vapor anymore, and also that a small amount of liquid bromine is left in the flask. How do you explain this? Here's the explanation. All the molecules in a liquid do not have the same kinetic energy. Some molecules at the surface of the liquid that possesses a relatively higher kinetic energy escape from the surface into the vapor phase. When the air inside the container is saturated with vapor, the molecules in the vapor phase condense to liquid as fast as the liquid evaporates. After some time, the number of molecules evaporating from the surface in a given time becomes equal to the number of molecules condensing on the surface during the same time. At this stage, equilibrium is said to have been established between the liquid and the vapor phase. This is why we see that the color of the vapor in the flask does not change. Thus, equilibrium may be defined as a condition in which two opposing tendencies balance one another. The equilibrium of liquid bromine with its vapor may be represented as Br2 liquid in equilibrium with Br2 gas. The pair of half-headed arrows indicates that the two processes, evaporation and condensation, are occurring simultaneously. At equilibrium, the rate at which the particles move from the liquid to the vapor phase will equal the rate at which the particles move from the vapor phase to the liquid. In this situation, the concentration of the vapor particles in the air space will be constant even though there is movement in both the directions. This equilibrium is, therefore, known as dynamic equilibrium. The opposing tendencies of a reversible change continue to take place with equal rates simultaneously at the equilibrium stage also. Hence, the equilibrium is called dynamic equilibrium. Equilibrium can be established for both physical and chemical processes. At the equilibrium state, if there is a change in the physical state, the equilibrium is called physical equilibrium. The important aspects of equilibrium involving physical processes can be understood by studying some phase transformation processes, such as solid-liquid, liquid-vapor, solid-vapor. Let's see solid-liquid equilibrium. Ice in equilibrium with water in a perfectly insulated thermos flask at 273 Kelvin and at atmospheric pressure stands as a perfect example of solid-liquid equilibrium. For this equilibrium, you can see that the temperatures as well as the masses of ice and water remain constant. Why is this so? Ice-water equilibrium is a dynamic equilibrium, where the number of molecules going from ice into water and the number of molecules going from water into ice are equal. As the rates of transfer of molecules from water to ice and from ice to water are equal, there is no change in the masses of ice and water. Since the system is insulated, no exchange of heat between the system and the surroundings is possible, and hence, the temperature remains constant. The equilibrium for this phase change may be written as H2OS in equilibrium with H2OL. It is important to note that ice exists in equilibrium with water only at a particular temperature and pressure. Thus, for any pure substance at atmospheric pressure, the temperature at which the solid and liquid are at equilibrium is called the normal melting point or normal freezing point of the substance. Let's now look at liquid-vapor equilibrium. Water in equilibrium with vapor in a closed vessel serves as a classic example of liquid-vapor equilibrium. Let's understand this through a simple experiment. A small amount of water is taken in a closed vessel to which a manometer is attached and left undisturbed for some time. After some time, you can see the slow increase of the mercury level in the manometer and the final attainment of a constant value. Did you also observe that there is a decrease in the volume of water in the vessel? How do you explain this? In the beginning, there was no water vapor inside the vessel. As water evaporated, the pressure inside the vessel increased, which was indicated through the rise in the level of mercury in the manometer. After some time, the level of mercury in the manometer remains constant, indicating that a state of equilibrium has been attained between water and water vapor. The molecules of the vapor in their movement collide with other molecules, with the walls of the container as well as the surface of the liquid. When some of the molecules with less kinetic energy come closer to the liquid surface, they get attracted to the surface. This process is called condensation. At any given temperature, evaporation and condensation take place simultaneously. After some time, the rate of evaporation becomes equal to the rate of condensation, and then liquid-vapor equilibrium is established. The pressure exerted by vapor over a liquid when it is in equilibrium with the liquid at a given temperature is termed as the vapor pressure of the liquid at that temperature. Water exists in equilibrium with its vapor at atmospheric pressure in a closed vessel. Thus, for any pure liquid at 1 atmospheric pressure, the temperature at which the liquid and vapor are in equilibrium is called the normal boiling point of the liquid. Let's look at solid-vapor equilibrium now. Some solid substances directly undergo a phase change from solid to vapor without the intermediate liquid state. This is called sublimation. Observe the solid iodine placed inside the conical flask and fitted with a cork. You can see the vessel getting filled up slowly with violet vapors. Have you observed that the intensity of the color has become constant? At this stage, we can say that an equilibrium state has been attained for the system. At equilibrium, the solid iodine sublimes to give iodine vapor, and the iodine vapor condenses to give solid iodine. The equilibrium can be represented as I2 solid in equilibrium with I2 vapor. You have learned that during physical process like phase transformation, it is possible to attain equilibrium. Similarly, when a physical process like dissolution is taking place, it is possible to achieve a state of equilibrium. There are two types of dissolution: gas in liquids and solid in liquids. Sugar in water is a classic example of solid in liquid equilibrium. First, sugar is added to a glass of water and stirred. It dissolves, forming a sugar solution. Then, as more and more sugar is added, it initially dissolves, but eventually reaches a stage where no matter how long you wait or how vigorously you stir, the sugar does not dissolve. The solution thus obtained is said to be saturated at the given temperature. Thus, at a given temperature, a solution that remains in contact with excess solute is said to be a saturated solution. In a saturated solution, a dynamic equilibrium exists between the solute particles in undissolved state and the solute particles in the solution. When the solution is kept in a closed system, the concentration of the solution and the amount of undissolved solute remains constant in the solution. The dynamic nature of this equilibrium can be established using radioactive sugar. Let's see how. Take a beaker containing saturated sugar solution. To this, add a small quantity of radioactive sugar and let the solution remain undisturbed for some time. Then check the solution for radioactivity. It is noticed that both the undissolved sugar as well as the solution has turned radioactive. This is a result of dynamic equilibrium, where the molecules of the radioactive and the non-radioactive sugar from the solid and liquid phases are being exchanged. This proves that there is dynamic equilibrium when a solid is dissolved in a liquid. Now let's look at the equilibrium involving the dissolution of gases in liquids. Have you ever wondered why soda fizzes when opened? The fizz that bubbles up when you open a soda water bottle is carbon dioxide gas. The phenomenon of fizz you see in carbonated beverages is due to the difference in the solubility of carbon dioxide at different pressures. At a given pressure, equilibrium exists between the carbon dioxide molecules in the gaseous state and those in the dissolved state in the liquid. This equilibrium is governed by Henry's law, which states the mass of a gas dissolved in a given amount of a liquid at any temperature is directly proportional to the pressure of the gas present in equilibrium with the liquid. All carbonated drinks are bottled under pressure to increase the solubility of carbon dioxide in the solution. When the bottle is opened, the pressure above the solution decreases. To reach the new equilibrium condition under decreased pressure, some of the dissolved carbon dioxide escapes. This gives rise to the fizz that you see when you open a bottle of carbonated drink. This is also the reason why the taste of carbonated drinks turns flat when the bottle is kept open for some time. Thus, we can summarize the general characteristics of equilibrium in physical processes as: at atmospheric pressure, a solid exists in equilibrium with a liquid only at one temperature, which is called its melting point. For example, at atmospheric pressure, ice exists in equilibrium at 273 Kelvin. At a given temperature, vapor pressure remains constant for liquid-vapor equilibrium. For example, in equilibrium between water and water vapor, the vapor pressure of water remains constant at a given temperature. At a given temperature, solubility remains constant for the dissolution of solids in liquids. For example, at the given temperature, the solubility of sugar remains constant in a given liquid. At a given temperature, the concentration of a gas in a liquid is directly proportional to the pressure of the gas over the liquid. For example, the concentration of carbon dioxide in water at equilibrium is directly proportional to the pressure of the gas over the liquid. At a given temperature, equilibrium can only be achieved in a closed system. For example, no equilibrium is attained when water in a beaker is kept open to the atmosphere. This is because the rate of condensation is much less than the rate of evaporation. At equilibrium, both the opposing tendencies occur at the same rate, and hence, a dynamic yet stable status is established. For example, for water at a given temperature in a closed vessel at equilibrium, the rate of evaporation is equal to the rate of condensation. At a given temperature, the attainment of equilibrium for a physical process is characterized by a constant value of one of its parameters, such as vapor pressure, melting point, solubility or concentration. For example, during equilibrium between liquid and gaseous water molecules, the vapor pressure of water remains constant at a given temperature. At equilibrium, all the measurable properties of the system remain constant. For example, for the solubility of solids in liquids, the solubility remains constant at a given temperature. Equilibrium in chemical processes, called chemical equilibrium, is the most important characteristic of irreversible reactions. The characteristics of chemical equilibrium can be understood only when you are familiar with certain terms, like reversible reactions and forward and backward reactions. So, let's get acquainted with these terms first. In general, the transformation of one substance into another is known as a chemical reaction. The chemical substances used at the initial stage during such transformation are called reactants, and the final chemical substances formed as a result of the chemical reaction are known as products. A reversible reaction may be defined as a chemical change in which the products can be converted back into the original reactants under suitable conditions. In a reversible reaction, The reaction in which the reactants react to give the products is called the forward reaction, while the reaction in which the products react back to give the reactants is called the backward reaction. Depending on the chemical nature of the products and the reaction conditions, the products formed may or may not react to give the initial substances. Let's take the example of the decomposition of calcium carbonate to demonstrate a reversible reaction. When calcium carbonate is heated strongly, it decomposes to form calcium oxide and carbon dioxide gas. When this decomposition is carried out in an open vessel, carbon dioxide, being a gas, escapes. Hence, there is no possibility for the products calcium oxide and carbon dioxide to react and give back the reactant calcium carbonate. Thus, the reaction proceeds in the forward direction only. Thus, the reactions whose products cannot be converted back into the reactants are known as irreversible reactions. When the same reaction of the decomposition of calcium carbonate is carried out in a closed vessel, the products, calcium oxide and carbon dioxide, combine to give solid calcium carbonate back. This clearly indicates that the reaction is capable of occurring in both the forward and the backward directions under favorable conditions. Such a reaction is called a reversible reaction. Reversible reactions are represented by a pair of half-headed arrows. If we plot a graph of a reversible reaction, we will notice that the rate of forward reaction is initially high. With the passage of time, the reactants deplete and the products accumulate. This leads to a decrease in the rate of the forward reaction and an increase in the rate of the backward reaction. After some time, a stage is reached when the rates of both the forward and the backward reactions becomes equal and the system reaches a state of equilibrium. We can graphically represent dynamic or chemical equilibrium as a forward reaction starting at a higher rate and a reverse process starting at zero rate coming together to reach an equilibrium point. Hence, when a reversible reaction is carried out in a closed vessel, a state is reached when the rate of the forward reaction becomes equal to the rate of the backward reaction. This stage is known as chemical equilibrium. It must be noted that the reaction can reach a state of equilibrium even if we start with the products, which is because equilibrium can be reached from either direction. The dynamic nature of chemical equilibrium can be understood by studying a gas phase chemical reaction. For example, when hydrogen and iodine are heated in a closed vessel, they react to form hydrogen iodide. When a mixture of equal initial concentrations of hydrogen and iodine are taken in a flask, maintained at 717 Kelvin, the intensity of the purple color decreases after some time. This is because, as the reaction proceeds, the concentrations of hydrogen and iodine decreases as they are consumed, and hence, the rate of forward reaction slows down. On the other hand, the concentration of hydrogen iodide increases with the progress of the reaction. As hydrogen iodide accumulates, the backward reaction of hydrogen iodide decomposing to hydrogen and iodine becomes significant. A stage is reached when the rates of the forward and backward reactions become equal, and the system is said to have attained equilibrium. At equilibrium, the concentrations of all the three species become constant. The graph depicts the variations of the concentrations of hydrogen, iodine, and hydrogen iodide as a function of time. You have already learned that in a reversible reaction, the reaction can reach a state of equilibrium even if we start with the products. Hence, the same state of equilibrium can be reached even if we start with hydrogen iodide alone. In this case, the concentration of hydrogen iodide will decrease and the concentrations of hydrogen and iodine will increase until they become constant at equilibrium. The attainment of equilibrium from either side can be shown in the form of a graph. The dynamic nature of the chemical equilibrium can be established by using radioactive iodine. When a small quantity of radioactive iodine is introduced into the above reaction in the state of equilibrium, it is found that the hydrogen iodide in the mixture contains radioactive iodine. This obviously shows that the reaction, though apparently standstill, is proceeding in both the directions. That is, the equilibrium is a dynamic equilibrium. Hence, the characteristics of chemical equilibrium are: equilibrium state can be approached from both the sides. The equilibrium is a dynamic equilibrium as both the forward and the backward reactions continue to take place with the same speed. At equilibrium state, properties such as pressure, concentration, density, or color remain unchanged over time. Equilibrium is possible only in a closed system. Consider the reversible reaction of nitrogen and hydrogen gases coming together to form ammonia. Is there any way to predict the extent of this reaction? Can we predict the direction of this reaction at any stage? Can we determine the equilibrium concentration from the initial concentrations for this reaction? These questions can be answered with the help of the equilibrium constant for that reaction. So, let's learn about equilibrium constant and its applications. In 1864, on the basis of experimental studies of many reversible reactions, two Norwegian chemists, Gullberg and Waag, established a relationship between the rate of chemical reaction and the concentration of the reactants and formulated the law of mass action. According to this law, at any instant, the rate of a chemical reaction at a given temperature is directly proportional to the active masses of the reactants at that instant. The term active masses in present times refers to molar concentration. In the early days of chemistry, concentration was called active mass. Hence, this law is known as the law of mass action. Let's see how it applies to the equilibrium state of a reversible reaction occurring in a homogeneous system at a given temperature. Let 1 mole of A react with 1 mole of B to produce 1 mole each of C and D. According to the law of mass action, the rate of forward reaction will be proportional to the molar concentration of the reactants A and B. That is, the rate of forward reaction Rf is directly proportional to the concentration of the reactants A and B. Or Rf is equal to Kf multiplied by the product of the concentrations of A and B, where Kf is the rate constant of forward reaction. Similarly, the rate of backward reaction will be proportional to the molar concentration of the products. That is, Rb is proportional to the product of the concentrations of the products C and D. Or Rb is equal to Kb multiplied by the product of the concentrations of C and D, where Kb is the rate constant of backward reaction. At equilibrium, the rate of forward reaction becomes equal to the rate of backward reaction. That is, Kf multiplied by the product of concentrations of reactants A and B is equal to Kb multiplied by the product of the concentrations of C and D. Or, this can be written as the product of the concentrations of products C and D divided by the product of the concentrations of reactants A and B is equal to Kf divided by Kb, which is equal to a constant Kc. Here, Kc is called the equilibrium constant of the reaction and is defined as the ratio of the product of the molar concentrations of the products to that of the reactants. The subscript C indicates that Kc is expressed in moles per liter. In the case that you just saw, the stoichiometric coefficients of the reactants and the products are unity. Now, let's consider a more general reaction of the type AA plus BB in equilibrium with CC plus DD, where A and B represent the stoichiometric coefficients of the reactants A and B, and C and D represent the stoichiometric coefficients of the products C and D, respectively. On applying the law of mass action, the rate of such a reaction is proportional to the concentration of each species raised to a power equal to the stoichiometric coefficient of the reaction. It, therefore, follows that at equilibrium, Kf multiplied by the product of the concentration of the reactants A raised to the power of A and B raised to the power of B is equal to Kb multiplied by the product of the concentration of the products C raised to the power of C and D raised to the power of D. This can be written as Kf divided by Kb is equal to the product of the concentrations of the products C raised to the power of C and D raised to the power of D divided by the product of the concentrations of the reactants A raised to the power of A and B raised to the power of B. This is equal to equilibrium constant Kc. Hence, the product of the concentrations of the reaction products raised to their respective stoichiometric coefficients in the balanced chemical equation, divided by the product of the concentrations of the reactants raised to their respective stoichiometric coefficients, has a constant value at a given temperature. This is known as equilibrium law or the law of chemical equilibrium. The equilibrium constant for the backward reaction is the inverse of the equilibrium constant for the forward reaction. Let us prove this with an example. Consider the reversible reaction of hydrogen and iodine combining to form hydrogen iodide. The equilibrium constant for this reaction is written as Kc equal to the concentration of the product, hydrogen iodide, raised to the power of 2 divided by the product of the concentrations of the reactants, hydrogen and iodine. Let us say this is equal to x. Now, the equilibrium constant for the reverse reaction, hydrogen iodide disintegrating to form hydrogen and iodine, is written as K-C is equal to the product of the concentration of hydrogen and iodine divided by the concentration of hydrogen iodide raised to the power of 2. Now, this is nothing but the reciprocal of x, which is equal to 1 by Kc. Thus, the equilibrium constant for the backward reaction is the reverse of the equilibrium constant for the forward reaction Kc. Chemical equilibrium may be classified into homogeneous equilibrium and heterogeneous equilibrium. The equilibrium in a system with all the reactants and products in the same phase is known as homogeneous equilibrium. Examples of homogeneous equilibrium include the reaction between hydrogen and iodine to form hydrogen iodide, the reaction between nitrogen and hydrogen to form ammonia, the hydrolysis of ethyl acetate to acetic acid and ethyl alcohol. This example represents homogeneous equilibrium in the liquid phase. The equilibrium in a system which has more than one phase is called the heterogeneous equilibrium. Examples of heterogeneous equilibrium include the thermal decomposition of calcium carbonate into calcium oxide and carbon dioxide, the displacement reaction between zinc and copper sulfate to give copper and zinc sulfate. The equilibrium constant in gaseous systems. For gases at constant temperature, the pressure of the gas is proportional to its concentration. Hence, for a reversible reaction involving gases, the equilibrium constant is conveniently expressed in terms of partial pressures of the reactants and products in place of molar concentrations. Let us now see how the pressure of a gas at constant temperature is proportional to its concentration. According to the ideal gas equation, PV is equal to nRT, or P is equal to nRT by V, where P is the pressure, N is the number of moles of the gas, V is the volume of the gas, R is the universal gas constant, and T is the absolute temperature. However, we know that N by V corresponds to molar concentration C. Therefore, the equation can be written as P is equal to CRT. Since R is constant, it can be written as at constant temperature, the pressure of a gas is proportional to its concentration. The equilibrium constant in terms of partial pressure is represented by Kp. Let us examine the relationship between the two equilibrium constants, Kc and Kp. For a general reaction of the type AA plus Bb in equilibrium with Cc plus Dd, the equilibrium constant is written as Kc is equal to the product of the concentration of the products C raised to the power of C and D raised to the power of D respectively, divided by the product of the concentration of the reactants A raised to the power of A and B raised to the power of B respectively. Now, if the reactants and products are gaseous, partial pressure may be used instead of concentrations. Then, the equilibrium constant in terms of partial pressure can be written as Kp is equal to the product of partial pressures of the products C raised to the power of C and D raised to the power of D respectively, divided by the product of the partial pressure of reactants A raised to the power of A and B raised to the power of B respectively. Since P is equal to CRT, it can be written as partial pressure of Pc is equal to the concentration of C multiplied by the product of R and T. Partial pressure of Pd is equal to the concentration of D multiplied by the product of R and T. Partial pressure of Pa is equal to the concentration of A multiplied by the product of R and T. Partial pressure of Pb is equal to the concentration of B multiplied by the product of R and T. Therefore, the equilibrium constant in terms of concentration can be written as Kp is equal to the product of concentration of the products C raised to the power of C, the concentration of D raised to the power of D multiplied by the product of R and T raised to the power of C plus D divided by the product of the concentrations of the reactants A raised to the power of A and B raised to the power of B multiplied by the product of R and T raised to the power of A plus B. This can be written as the product of the concentration of the products C raised to the power of C and D raised to the power of D divided by the product of the concentration of A raised to the power of A and B raised to the power of B multiplied by the product of R and T raised to the power of sum of C and D minus sum of A and B. This becomes equal to the product of the concentration of C raised to the power of C and the concentration of D raised to the power of D divided by the concentration of A raised to the power of A and the concentration of B raised to the power of B multiplied by the product of R and T raised to the power of delta N. Since the product of the concentration of C raised to the power of C and the concentration of D raised to the power of D divided by the concentration of A raised to the power of A and the concentration of B raised to the power of B is equal to equilibrium constant Kc. This can be written as Kp is equal to Kc multiplied by the product of R and T raised to the power of delta N, where delta N is equal to the number of moles of gaseous products minus the number of moles of gaseous reactants. Thus, Kc and Kp are related to each other by the equation Kp is equal to Kc multiplied by the product of R and T raised to the power of delta N. Let us see how the relationship between Kp and Kc varies with the difference in the number of moles of products and reactants. Case 1. When delta N is equal to 0. Consider the reversible reaction of hydrogen and iodine that gives hydrogen iodide. For this reaction, the difference in the number of moles, delta N, is equal to number of moles of hydrogen iodide minus number of moles of hydrogen and iodine, which is equal to 2 minus 2 is equal to 0. Substituting the value of delta N in the equation, Kp is equal to Kc multiplied by the product of R and T raised to the power of delta N. We get Kp is equal to Kc. Thus, for reactions in which delta N is equal to 0, the two equilibrium constants Kp and Kc are equal. Case 2. When delta N is negative. Consider the reversible reaction between nitrogen and hydrogen that gives ammonia. The difference in the number of moles for this reaction, delta N, is equal to number of moles of ammonia minus number of moles of nitrogen and hydrogen is equal to 2 minus 4 is equal to minus 2. Substituting the value of delta N in the equation, Kp is equal to Kc multiplied by the product of Rt raised to the power of delta N. We get Kp is equal to Kc multiplied by the product of R and T raised to the power of minus 2. Therefore, for reactions in which delta N is negative, that is, where the number of moles of gaseous products is less than the number of moles of gaseous reactants, Kp is less than Kc. Case 3. When delta N is positive. Consider the dissociation of phosphorus pentachloride into phosphorus trichloride and chlorine. For this reaction, the difference in the number of moles, delta N, is equal to number of moles of phosphorus trichloride and chlorine minus number of moles of phosphorus pentachloride is equal to 2 minus 1 is equal to 1. Substituting the value of delta N in the equation, Kp is equal to Kc multiplied by the product of R and T raised to the power of delta N. We get Kp is equal to Kc multiplied by the product of R and T raised to the power of 1. Therefore, for reactions in which delta N is positive, that is, where the number of moles of gaseous products is more than the number of moles of gaseous reactants, Kp is greater than Kc.